Welcome to the Explainer. Today we're diving into a mathematical idea that for centuries seemed totally abstract, just a quirk of pure thought. But as you're going to see, this imaginary concept is actually one of the most powerful tools we have for describing the very real world around us. I know, it sounds like something straight out of science fiction, right? But this is the strange reality we're going to explore. We're about to see how an idea that was born from an impossible equation underpins everything from how water flows to how electronics work. For the longest time, this equation right here was a brick wall. In the world of numbers we use every day, the real numbers, there's just no number that, when you multiply it by itself, gives you -1. A positive times a positive is positive, and a negative times a negative is also positive. It was a complete dead end. So mathematicians did something audacious. They just asked, well, what if there was a solution and they just invented one? They called it I for imaginary and simply defined it into existence as the square root of -1. A simple act of imagination that honestly would change absolutely everything. Because here's the thing, this little number I doesn't just solve one little nagging problem. No, it completely blows the doors open on our whole concept of numbers, giving us an entirely new dimension to play with. We're talking about the complex plane. We all know the number line, right? That one single dimension holding all the real numbers. But now, with I, we can draw a second axis, perpendicular to the first. This is the imaginary axis, a dimension built on multiples of I. And just like that, our number line has become a whole number plane. And now every single point on this brand new plane is what we call a complex number. It has a real part, x, which is its horizontal position, and an imaginary part, y, for its vertical position. Just think about that for a second. We can now describe any point on a 2D map with just a single number. Okay, so we can define points. But the real power, the real magic, comes when we start applying functions to these points. This isn't just about calculation anymore. It's about transformation. We can literally reshape the entire plane. I want you to think of a function, something like w equals f of z, as a kind of machine. You feed it a point, or heck, a whole shape from one complex plane. We'll call it the z-plane. And it maps it to a new location, a totally new shape in a second complex plane, the w-plane. It stretches, it rotates, it warps the input. Let's take a simple one, like w equals z squared. If you feed in a standard grid of straight lines, what comes out on the other side? Well, it's not a grid anymore. The function beautifully warps those straight lines into this elegant new pattern of intercepting curves. That's what we mean by transformation. Okay, this is elegant. It's really fascinating. But I know what you might be thinking. It still feels like a purely mathematical game, right? Like some kind of abstract art. Does any of this actually connect to the real physical world? Well, this is the moment. This is where the curtain gets pulled back. Because this imaginary math isn't just abstract geometry. It turns out to be the native language for some of the most fundamental laws of physics. To really see this connection, we need to meet what are called analytic functions. You can think of these as the VIPs of the complex world. They're incredibly smooth. They transform the plane without any sudden tearing or folding or sharp corners. They're just really well behaved. And our second key idea comes from physics, harmonic functions. Basically, these describe things that are in a state of balance or equilibrium. Like how heat spreads evenly across a metal plate, or how voltage stabilizes in an electric field. It's the math of things that have settled down. And here it is. This is the incredible, almost unbelievable link. If you take any of those smooth analytic functions and you just separate out its real and imaginary parts, both of those parts, on their own, are guaranteed to be harmonic. They automatically describe a system in perfect physical balance. You see, this isn't just a coincidence. It's a bridge. It lets scientists take a really messy, real-world problem, walk it across this bridge into the elegant world of complex math, find a clean, simple solution, and then bring it right back. And the list of physical systems described by these harmonic functions? It's huge. We're talking about how heat gets distributed, how liquids flow, the behavior of electric fields, even certain kinds of waves. All of them obey this same math of steady states. So here's the genius strategy. You take a physical setup that's really hard to analyze, maybe it has a complicated shape. Then you find the right analytic function, your transformation machine, to warp that difficult shape into something incredibly simple. For example, figuring out the path of water flowing around a round pipe, that's a nightmare. But there are analytic functions that can mathematically unroll that pipe into a simple flat line. And calculating fluid flow over a flat line, well, that's incredibly easy. So it becomes the simple three-step recipe. First, you map the hard problem to an easy shape. Second, you solve the problem there, which is often trivial. And third, you use the inverse of your mapping function to transfer that simple solution right back onto the original complex shape. You've just solved a real-world physics problem using imaginary numbers. It's amazing. So let's just step back for a second and appreciate what just happened here. An idea that started out as what seemed like a mathematical fiction has become an absolutely indispensable tool for engineering our world. Think all the way back to the beginning. It all started with the simple act, taking our familiar one-dimensional number line and adding a second dimension, all based on that one little imaginary number. And that single leap from one dimension to two gave us this unbelievably powerful bridge, linking the abstract world of pure math directly to concrete, practical solutions for the physical world we actually live in. You know, this power, it hints at something that's almost like a holographic principle. For these special analytic functions, if you know what's happening just on the boundary of a system, you can perfectly determine everything happening on the inside. It's an incredible statement about hidden connections and predictive power. It just goes to show that sometimes the most practical tool you can possibly have is a powerful imagination. And it leaves us with this huge question, right? What ideas dismissed today as merely abstract or imaginary are just waiting for us to discover that they are, in fact, the key to understanding our universe?